Okay, so it's just taking a couple of seconds. Okay, so we're recording now. I'll just share my screen and then we can begin. Okay, so I'm using the same data set. Today we'll be evaluating the accuracy of our forecast. Okay, so before we get into forecast accuracy, in case anyone is following along with me, just use the R script that I had mailed you all the last time. Okay, and run these basic commands. You don't have to run all the commands. Just load all the packages. Okay, then import your data set. I'm using the same data set as the previous time. Okay, so just run the same basic commands. Tell R that your data is time series data, then compute the returns. Okay, after that, I'll quickly just seasonally adjust my data and use the seasonally adjusted data for analysis. Okay, then I'm dividing my data into the training set and the test set so that I can carry out of sample forecasting. I'm skipping the entire portion on stationarity test since we've already done the checks, and I'm just straight away running model 4, okay, which was the best fitting model assuming that the time series is stationary. And I'm also running D mod 3. Okay. If I go with some of the odd conclusions that we had from the stationarity test, which declared that the time series was non-stationary, I fitted a model based on that finding. So this was the best fitting model in that case. So I'm just running that as well. And then I'm generating my forecast based on D mod 3. Okay, so for this portion, it's not so important for all of you to follow along. But in case you want to, it's fine. You can go ahead and follow. So before we actually discuss the accuracy and calculate the accuracy of our forecasts, okay, let's quickly look at what are the theoretical concepts related to this. Okay.
Ma'am?
Yes?
Do we have to do the accuracy test in our assignments as well?
No, you don't have to.
Okay.
Okay, so since this is being taught in today's class, I will not be evaluating you on the accuracy part of it. If you want, you can include it in your code, but you need not. Okay, you will not be evaluated at all on that part, even if you include it. So one of the measures that we use, there are several such measures which we use to evaluate the accuracy of our forecasts. Okay, one such measure is known as the mean absolute error. Okay, this is visible to all of you?
Yes, ma'am.
Okay. So one such measure is known as the mean absolute error. Okay. So here you take the absolute error or forecasting error that you get, which is the difference between the actual value of the time series at that time. Okay. For example, our first forecast is related to 2019 quarter 1. So I'll be taking the actual value of the time series at 2019 quarter 1 minus my forecasted value. Okay. So that will give me the forecast error. So if I take the absolute value of these errors, suppose I've generated, in our case, we've generated 9 such forecasts, okay, 9 steps ahead. So if I find out the mean of these forecasting errors that I've made, the mean of the absolute value of the forecasting errors, I'll get the mean absolute error. So here one thing that you'll notice is that these errors are on the same scale as the data, as in they'll be measured in the same units as the original time series. So this is a scale dependent measure of forecast accuracy. If you use the mean absolute error, this measure will be dependent on the scale in which you're measuring the time series or the units in which you're measuring your time series. So this is one such measure for forecast accuracy, and naturally you all would have understood that the smaller the mean absolute mean absolute error, the better your forecast will be. Okay? Now, a concept which is somewhat similar is to take the mean of the errors itself, not the absolute errors, but here the mean of the squared errors, and then find out what is the square root of the mean squared errors. So this measure is known as root mean square error. Okay. So this is also one of the most frequently cited measures of forecast accuracy, and this is also a scale dependent measure. Okay. Since it will be measured in the units of the time series itself, so this is also a scale dependent measure. So you cannot use it to compare forecasts for two time series which have different units of measurement. Okay. Then a third measure of forecast accuracy is mean absolute percentage error. Okay. So first you need to find out what is the percentage error itself, okay, which is given by this formula PT. This is your forecast error, the difference between the actual value of the time series, okay, and the forecasted value. So that will give you the forecasting error. Divide that by the actual value of the time series into 100. Okay. So this will give you the percentage error, and then if you take the absolute value of the percentage error and find out the mean of these absolute values, you'll get the mean absolute percentage error. So here one thing that you might have noticed is this is a unit free measure. Okay, so this does not depend on the scale since the units cancel out. So this is a measure which is independent of the scale of the time series or unit of measurement of the time series. So in that way, it has certain advantages in the sense that you can compare forecasts for two different time series which have different units of measurement. So you can use this MAPE to calculate or to compare the forecast accuracy for two different time series which have different measurement units. But one disadvantage is that in case YT has a value which is 0 or very close to 0, okay, in that case, your percentage error will be undefined or it could be infinite in value, which becomes problematic. So these are certain issues related to mean absolute percentage error. Then another measure of forecast accuracy is known as the mean absolute scaled error. Okay. So here what is done is the forecast error is scaled by the average of the naive forecasts. Okay. So if you take your training data set, okay, not the test set, but the training data set, and then find out the naive forecast, okay, naive forecasting error. So for example, if you take, in our case, the training data set, and then assume that all your forecasts, okay, for YT, which is all the YT hats that you get, okay, those are equal to naive forecast, which means that the value of the last observation in your training set, that will be equal to the naive forecast. So if you find out the difference between the actual value of the time series and the naive forecast from your training data set, and then find out the mean of such forecasting errors if you use the naive forecasting method. Okay. So then you will get this measure, mean absolute scaled error, where you're scaling the error or dividing the forecasting error by the average naive forecasting error from your training data set. Okay? If you look at the formula, you'll be able to understand what it means. So for example, if in our training data set, we were using T observations. Okay? So then here, if you start from 2, okay, up to n, since you need at least one observation in order to make your forecast, you're starting from 2 up to n, okay, where n is the end of your forecasting horizon. So here y1, for example, this will be y2, okay, the actual value at time period 2 in your training set, and this here will be the naive forecast. For example, in this case, it will be the value of y1, since you will be forecasting according to the last observed value. So just the previous value of the observed time series. So this will give you your naive forecasting error. Okay? Then if you find the mean of such errors, okay, and divide your forecasting error from the test data set, if you divide that, okay, sorry, not from your test data set, but from the out of sample forecast. So if you divide your forecasting error by the average naive forecasting error, the mean of the average naive forecasting errors, then you will get the mean absolute scaled error. Okay? So this again is a unit free measure, or it is not dependent on the scale of the time series. Okay? So this is one advantage, but this also has similar problems in case the value of y at any time period, if it's equal to 0, then it becomes problematic. Or if this difference is equal to 0, then it becomes slightly problematic. Okay? Then a last measure that we'll be discussing is known as Thiel's U statistic. Okay? So this is also very often cited in the literature. You'll find that this measure is used to compare the accuracy of the forecast very often. So here this involves simply, in some sense, you can think of it as comparing the mean forecasting errors, okay, from your out of sample forecast with the mean forecasting error if you use a naive forecasting method. Okay. So in the numerator, here you'll have your own forecasting errors which you get from your out of sample forecast. Okay. For example, in our case, all the forecasting errors that we get for F1, since F1 are the forecasts that we generated. So if you compare all the values in F1 itself with the actual values of the time series, okay, from the test set, you will get your forecasting errors. So this numerator part relates to our out of sample forecasting errors, okay, and the squared values of these forecasting errors, and then taking the sum of those squared values. Then the denominator part of it relates to the naive forecasting method. So what would be the forecasting errors you would make if you were using the naive forecasting method to make your forecast? Okay. Again, find out the square of those errors and the sum of the squared errors. So taking the ratio of these two methods, your own out of sample forecasting errors by the forecasting errors from the naive method, okay, that will give you Thiel's U statistic. So in there are certain people who also refer to it as comparing the RMSE from your own forecasting method with the RMSE from the naive method of forecasting. So that is an equivalent way of looking at Thiel's U statistic. There's no real difference between the two. Now, what you'll understand, especially from these last two methods, is that if, for example, Thiel's U statistic, the value of this statistic is equal to 1, okay, that means that your forecasts, when you're creating these out of sample forecasts, your own forecasts are about as good as the forecast made from a naive method. Okay, so your forecasts are as good as guessing, where your guess is based on the last observed value of the time series. But if you find that the value of the U statistic is less than 1, That means that your forecasting errors are smaller compared to the forecasting errors from the naive method. So your forecasting method is actually better than the naive forecasting method. So you can stick with your own forecast. Okay, this is if u is less than 1. Now, if u is greater than 1, it means that your forecasting errors are larger than the forecasting errors produced from the naive method. So it's better, or essentially it's worthless to use your own forecasting method. Okay? And it's better to rely on the naive forecasting method because that is giving you smaller forecast errors. Okay? So this is how you'll interpret the value of Thiel's U statistic. This also has a similar interpretation. Okay? So if this is equal to 1, your method is as good as the naive method. If it's less than 1, your forecasting method is an improvement over the naive forecasting method. If it's greater than 1, your forecasting method is worse than the naive method. So it's better to rely on the naive method itself. Okay? So this is how you will interpret these methods of, measures of forecasting accuracy. So today we'll just look at how we actually calculate these measures, and then we'll go ahead and discuss the results that we get. So I'm running the code from this file. I've already saved the commands. Okay, so after generating the forecast, I'm just running this command. I've already segregated my data into the training set and the test set. Just let me know if you have any doubts or questions at any point. So what you will notice is that even when you were actually generating the model results, for example, let me see here. Okay, so after I ran D mod 3, if I had typed summary of D mod 3, you will find that these same measures of forecast accuracy are available here even for the training set. Okay? So this is just the mean error. This is the root mean square error, mean absolute error. Okay? Then this measure we haven't discussed. You can leave it out for now. This is the mean absolute percentage error. Then mean absolute scaled error. Then the ACF at the first lag. Okay? This is related to the residuals from your model. So you'll notice that these same measures pop up even for your model results. Okay, but today we'll be discussing how they are related to your out of sample focus. So I'll quickly look at those results. Okay. So if you look at this portion, where I've compared the accuracy of my own focus, okay, from the model D mod 3 with the test set. So test 1 has the actual data on the time series from 2019 quarter 1, okay, till the last observation that we have for our sample. So here if you look at this portion, test set, okay, so this gives you the mean of the errors, the mean error, then the RMSE. The RMSE is quite small. It's better than the RMSE for your training set also. Then mean absolute error also is smaller compared to your training set, but it's generally probably not fair to compare with the training set itself. Okay? Just look at the values itself. They should be as small as possible. Then if you look at this portion, the mean absolute percentage error. So this appears to be quite a high percentage error that we are getting. Okay, the mean is quite large. Then for mean absolute scaled error. Okay? So these, you will find the interpretation somewhat easier compared to the other measures. Okay? So if you look at the mean absolute scaled error, if the value was equal to 1, it means that our forecasts are as good as the naive method of forecasting. Okay? It's not an improvement over the naive method, but here since you find that our forecast errors are quite small compared to the average naive forecast from the training set. Okay? So the value is less than 1. So you can conclude that our forecasts are actually better than the naive method of forecasting, okay, from the training set itself based on this value. Since it's less than 1, the mean absolute scaled error, you can interpret your result this way. Okay. Then if you look at Thiel's U statistic, again you will find that the value is less than 1. Okay. So if you remember the plot of our forecast, it didn't look very good. Okay. They couldn't actually plot the trajectory of the time series in the test set. Okay. Let me just show you quickly. Okay, so this was our forecast from D mod 3, and this was the test set. So this is the actual data and these are our forecasts. So just by looking at it, you can see that our model is not forecasting very well because it cannot actually capture the patterns in the data in the test set. Okay. So based on just looking at the graph, you might think that your forecasting effort was worthless, okay? But don't just rely simply on the graphs. What you need to do is check using the measures of forecast accuracy. So what you will find here, let me go back here. Okay, since both mean absolute scaled error and Thiel's U statistic are less than 1, so your effort was not a waste. Okay, so your forecasting method is definitely better than the naive forecasting method, so you can take some heart in that fact. Okay, and you can rely on your forecast. So there could be some peculiarities in this data set because of which we have not been able to forecast very well, but still our forecasts are not that bad. Okay. Any doubts or questions related to this? How do you interpret the forecast accuracy measures? Any doubts or questions?
Ma'am, I have a doubt.
Yes.
And for maze, we are comparing it with 1. Like if it is less than 1, so we can say it's not as bad as a forecast. What about the other values? What are we comparing it to?
You will not be able to compare it to anything as such unless you have another time series which is on the same scale. Okay. Or if you use a different model but with the same sample size. For example, if you have two different models with different specifications, for example, this is ARIMA 011, right? Okay. So if I use the exact same data, which begins from 2009 quarter 2, ends with, let's say, 2018 quarter 4, right? Okay, so this actually, since you're taking a difference here, it will begin from 2009 quarter 3, okay? And then it ends in 2018 quarter 4. So if you used another model, for example, if I used ARIMA 111, okay, using the same data, 2009 quarter 3 to 2018 quarter 4. So then if I generated the RMSE for the forecast from that model, I could compare it with this model, okay, and see which is giving better forecasts. So that is something that I can do. If I use a different model, then I can do that sort of a comparison, but again, based on the same time period. Now, if I take mod 4 itself, if you look at mod 4, okay, this is 101. So here I'm not differencing my time series, so I haven't lost one observation. So my data set is actually starting from 2009 quarter 2, not from quarter 3, starting from 2009 quarter 2 and ending in 2018 quarter 4. Now if I take the forecast from this, okay, and then compare it with D mod 3's forecast, okay, that will not be fair because this model is based on 2009 quarter 3 data onwards, okay, whereas the other model is based on 2009 quarter 2. So there I cannot make comparisons. If I have the same time period but two different models, if I have ARIMA 111 and ARIMA 011, then I can compare the RMSE of this model with ARIMA 111. Okay, and whichever has a lower RMSE, I can prefer that model over the other model. So that is how I'll interpret my results in that case. Okay. Just make sure that you're comparing data which have the same units if you're using measures like RMSE, MAE, and so on. And also they should be for models which have the same time period, not different time periods. Then you can make the comparison.
Understood. Thank you.
Okay. Any other doubts or questions? Okay, now these measures, you'll find it at the end of every model's result. You'll find the same measures for your training set. So this is related to the errors from your regression itself. Okay, since they are in sample forecasting errors, if you look at this plot that I generated, I didn't show you all this in the previous class, but I sent it in the code. So if you have run the code, you'll be able to see this. Okay, so these are the forecasts from your fitted model. So this is from D mod 3 on the training set itself. So these are your fitted values or your YT hats that you have generated, okay, from the model. And then the actual data is in orange over here. So based on this, you can see that your model is actually not performing that badly. It's trying to mimic the patterns in the data, but it's not very successful. Okay. So based on in-sample forecast performance, you can look at these measures of forecast accuracy. Okay. All these measures, and then you can understand how accurate your forecasts have been. So for example, this again is you can compare it to the average naive forecasting method. It's less than 1. So you can conclude that your in-sample forecasts are better than the naive forecasting method, okay, based on the training set itself. So this way you can interpret the accuracy of your in-sample forecast itself using these measures. Okay, but generally we evaluate for out-of-sample forecasts. Okay, that is the general practice. So you can use this command to generate these accuracy measures and then compare your forecasting performance with the actual data. Okay. Now what we'll do next is look at structural breaks in the data or structural changes in the data. Okay. Now the reason that I'm using the same data set for this is something that I pointed out at the end of the previous class. Let me see here. So if I've already run this command, so I will not run it again. So here I'm seasonally adjusting my return series using X13 seats. Okay, that's the command that I'm using. So I've already seasonally adjusted the data. So I'll simply plot the data so that you can see what I'm talking about here. Okay. So here, if you look at this second portion of your graph. Okay. So here, if you look at the trend, you will see that there seems to be some sort of a break in the trend. So up to somewhere around 2015, you'll find that your trend probably had an intercept of 4. Okay. And the slope is essentially 0, but the intercept is 4. And here after 2015, there seems to be a break in the intercept or a change in the intercept. Now it's fallen to 2. Okay, now this is simply based on the results from X13 seeds, but we need to verify whether there's actually a break in our data or some sort of a structural change in our data. So that is something that we'll be doing in today's class. Now, before we actually move on to that, I realized that I hadn't mentioned this explicitly. So in case some of you need to detrend your data, remember that for any time series, okay, the reason for non-stationarity could be that it has a stochastic trend. So if your data or time series has a stochastic trend, that means it is different stationary. Okay, so the data as it is non-stationary, but if you take the first difference, then it will become stationary. Okay? Whereas if it has a simple linear deterministic trend, then in that case it is trend stationary, and you can simply make the data stationary by detrending the data. Okay, so there's a difference here. If the data has a stochastic trend, you need to difference the time series to make it stationary. If it has a linear deterministic trend, then you need to detrend the data to actually make it stationary. Okay. So now I'll just show you how to extract the trend itself. Some of you might have done this already. I had mentioned it, but just to be explicit in case somebody did not realize it. Okay. So let's simply plot the trend from this. So if you use the command trend and SAR1, okay, we've saved the decomposition results from X13 seats in SAR1, in this object SAR1. So I can use this command to actually plot only the trend of the data. Okay. So this will give me the trend. So if I want to extract the trend, okay, I'll simply use trend SAR1 and use that for the extraction. So if I need to detrend my data, then I'll just take, for example, train 1. Let me just call it detrend data. And you can subtract SAR1 from this. Okay. So this will give me the detrended data. Okay, now I can just plot this. Okay, so this gives me a plot of the detrended data itself. Okay. So if you need to do this, if you have a linear deterministic trend in your time series, or if there's a deterministic trend, then you will detrend your data. Okay, and that will make the time series stationary. But instead, if there's a stochastic trend, then you need to difference your data. So just keep this difference in mind. Another thing, instead of using this seasonal adjustment technique, you can simply actually generate or create the trend variable yourself. Okay, so just create a variable t, okay, which runs from 1 to, since we have, I think, 48 observations in R1.
Ma'am, I have a doubt.
Yes?
So, ma'am, what we've done out here, we basically just subtracted the trend from the data that we have.
Yes.
So, ma'am, this we are using X13.
Hmm.
So, ma'am, when we use the stats, there's a function called decompose. What method does that use? Because decompose also does the same thing, like a
Yes.
similar thing, but not the same.
Yeah, so this, I think I've mentioned it at least 2-3 times. So just try and remember this aspect, okay? Maybe you weren't there in the class. So decompose, if you use it just like that, the command, that is the classical decomposition method. Okay? So in that, to calculate the trend, they use moving averages. So this is something that we did when we were using the air passengers data. So we used moving averages to actually calculate the trend, but that resulted in a loss of observations. Okay? If I remember right, we lost some 12 observations or something like that in the process because we are using moving averages.
So, ma'am, actually, ma'am, what happened was, I also tried I removed the seasonality using SEAS.
Hmm.
But, ma'am, then again, if I take that same data and I make it run through the SEAS, then again it shows that there is some amount of seasonality. So I'm a little confused as to why that is happening.
How did it show that it has seasonality?
Ma'am, because when I did the auto plot, it was showing it was showing like a diagram.
Mm, that's fine. There's no problem with that. For example, here you're saying that there was a pattern.
Yes, ma'am. Even after I removed the seasonality, and
That's okay.
actually, ma'am, I'm using X11 because X13 is not working on my data. I don't know why.
Okay. That's fine actually, because here in our time series, this is a special case, okay, where using X13 we found that there's no seasonal pattern at all. Okay. So that's why you have just a straight horizontal line here at 0. There's no seasonal pattern. That's why it's looking like this. But in any other time series, you will find that there's some sort of up and down pattern like this. Okay, some repetitive pattern will be there. So that is just showing you the seasonal pattern in your data, and the adjustment has been done. For example, here if you use this command, that final
command.
one, yeah.
Yes, ma'am.
So that will give you a seasonally adjusted series, and there won't be any seasonal pattern, okay? Or it might not eliminate all the seasonality, but it has done the adjustment, so you don't have to worry about it.
All right, ma'am. All right. So ma'am, basically from SAR1, if you want to extract, we can extract this trend, we can extract the seasonal, and we can just we have to use the commands like you mentioned in that code right now, trend bracket open
Yes.
SAR1.
Yes.
All right. All right.
Okay. So this is just a special case where there was no seasonal pattern in the data. That's why it's looking like this. But otherwise, you will have some pattern being shown.
Ma'am, in my case, X11 and X13, both of them showed the different result. Like in X11, it was showing some seasonal pattern was there, but in X13, it was like this only, horizontal line. So
that's okay. You can choose either one and continue with that.
okay, ma'am.
So yeah, so this is from 1 to 39. We'll just use for the training data set, all right? Okay, so here I've simply basically created a variable called time, okay, which is just running from 1 to 39. So you have numbers running from 1 to 39. Then what I can do is to extract the trend. I'll just call it now simply regress your time series on this variable. Okay. Now if I extract the residuals from this and plot them. Okay, so this I'm basically regressing my time series on time, okay, on the trend basically. Okay. And then after that, if I extract the residuals and plot them, you'll find that this part, model 1 residuals, it actually gives me the detrended data. Okay, because if I subtract train 1 minus the coefficient here, I'll basically get the detrended data from the residuals of the model. Sorry. Okay, let me just use plot. Okay, so these are my detrended data points. Okay, it's in the form of points, but basically it will give you your detrended data. Now, suppose I suspected that it was actually not a linear trend, but a non-linear trend. Then what I can do is simply create two additional variables. Okay, so I'll create t square I'm just squaring that particular variable. Okay. So suppose I assume that a cubic function will better fit the data. Okay, then I can create these additional variables and then run my model on that. Okay. So once I run this command, I'll just look at the results to see which of these is better. Okay? Whether a linear trend fits the data better or is it a polynomial trend. So here for the linear trend model, what I find is that my trend is significant, okay? Which means that a linear trend seems to fit the data well, but I won't know unless I also compare with the polynomial trend model. Okay? So in this case, what I find is that if you look at the significance of the coefficients, this model does not seem to fit the data well. Even the linear trend coefficient is insignificant, and the squared term and cube term are also insignificant. Okay, so probably a linear trend model will fit the data better than the other type of model. Okay. So you can compare this way by looking at a plot of the data itself. You will be able to understand whether a linear model fits the data better or some other polynomial trend model fits the data better. Okay. So if you look at, sorry, this is a return series. Okay. Sorry, I should have done this with RPI and not with the return series. Okay, so that is showing a clear trend. Okay, so I'm just quickly overwriting the results. Yeah, since my t variable is running from 1 to 39 here, okay, that's why it's creating a problem. So I'll just make this 1 to 49. Okay. Now I'll just quickly look at the summary. So intercept is significant, even the trend is significant. So you can conclude that a linear model fits your data well. Okay. Now I can just try and plot this. So I'll plot RPI. Okay. Let me just try this. I don't know if it'll work. The same problem is happening. So I'll just sorry about that. Let me just plot the results from the model. So this shows you a linear trend, okay, for RPI itself. Okay, but this does not seem to fit the data well, because if I plot RPI, you'll see that the plot of this data is looking different. Okay. Sorry, this is the detrended data. So if I plotted the fitted values, you'd get a plot of the trend that I fitted itself. Okay. Yeah, so this seems to approximate the data quite well. I'll just repeat this so that in case somebody is confused because I went over it. Okay. So this is RPI, or original data on the price index itself. And this is the fitted values from the trend model. I fitted a linear trend to the data. So this gives me the fitted values from that model. And you can see that it seems to approximate the data quite well. Okay. And if I plot this, okay, the residuals from the model, this gives me the detrended data. Okay. So you can use these commands to actually fit the model. Now I'll quickly show you I'll have to create these variables again, all right? So Okay, so instead of this, if I use a non-linear trend for the data itself, cube. Sorry. This is still t square. I forgot to change the left hand side of it. So now it should work. So now if I plot the fitted values, you'll be able to see what it looks like, the trend that we have fitted, the nonlinear trend. But before that, let's just go to the results from the model itself to see whether a nonlinear trend fits the data better. So it seems to fit the data well in this case. Let's just plot it and see. So perhaps a nonlinear trend itself is appropriate for the data. Yeah, so this is the nonlinear trend that we fitted. It seems to do quite well when it comes to the data. So perhaps we can stop with t cube. Okay, a cubic function for the trend might actually approximate the trend in the data quite well. So this way you can generate the trend for yourself and then detrend the data using the residuals from the model. Okay, once you fit the trend. So if you want to do this sort of exercise where you fit a linear trend or a polynomial trend, then you can go ahead and do this. Otherwise, you can simply use the command from C's. Okay? Since that does the job of extracting the trend for you, you can do that. But in certain other cases, you might want to do this. Now, suppose you fit an additional term, a model with t, let's say, raised to the power 4. And in that case, if you found t raised to the power 4, the coefficient attached to that is insignificant, then you will drop that particular explanatory variable from your model and then fit a model using only t, t square and t cube. So fit as many terms as possible and then see which ones are insignificant, drop those terms. So you'll be able to actually pare down your model and find the model with the best fit for your data. Okay, so this way you can fit a linear time trend or a polynomial trend to your data and you'll be able to estimate using the detrended data. Okay, this is only in case you need to detrend the data, just keep that in mind. Any questions or doubts so far?
So ma'am, this structural break in the data you mentioned, the
Yes.
mean shifting from 4 to about 1.5, that is automatically taken care by this detrending of the data?
Actually, in this case, what I found was detrending the data creates a problem. I think one of the students had a similar problem. So when I noticed this trend, I thought that maybe detrending the data will take care of the structural break problem. So I detrended it. But the problem is that my time series got reduced to something similar to a white noise series. So it wasn't showing any pattern in the ACF, PACF. So the best fitting model was actually turning out to be an ARIMA 000 model. So I couldn't fit any ARIMA model to the data. So probably detrending the data was not the right way to go. Okay, so if my data was non-slip, just
What
1
if,
minute. 1 minute, let me
sorry.
complete. So if I had assumed that my data had a deterministic trend and that's why I was detrending it, so that assumption was wrong. Okay, that's what I found from my little exercise that I did by detrending the data. Okay. Yes.
Ma'am, I had the same problem. The thing was,
Yes.
without detrending, the auto ARIMA command was giving me ARIMA model of 010. So, which is basically a random walk with drift, right?
0, 1, yeah. Yes.
So, I am getting the same problem. And
If you had a constant term or intercept term, then it's random walk with drift. Otherwise, it's just random walk.
So a random walk, ma'am, right? Basically,
Yes.
0, 1, 0.
Yes.
So, but ma'am, when I look at the PACF and ACF of the untrended data, the non-detrended data, it looks like an AR5 process. But the auto ARIMA actually fits it using a 0, 1, 0 model, and the results of the auto ARIMA are actually lower than the AR5 process.
Lower, matlab, what do you mean by that?
In a sense, for example, the BIC is higher, the mean absolute percentage error is higher for the 0, 1, 0 model compared to the AR5 model. But R is only fitting 0, 1, 0 model.
Why are you looking at mean absolute percentage error?
Ma'am, I'm looking at all the statistics, all the errors.
Okay.
Like MAP is just one of them.
Did you look at AIC?
Yes, ma'am. AIC and BIC for the AR5 process are both lower than the 0, 1, 0 random walk process.
Okay. So which one did you select then?
Ma'am, in my assignment, I've done both. So
Yeah,
you
but
can
you
pick.
have to select one, right? Finally.
So, ma'am, finally, I've selected like AR1 to AR5 to use for the forecast.
Okay, fine. Based on AIC.
Yeah, AIC and BIC.
Okay, fine. So auto ARIMA might not always give you the best result because it's using an algorithm, so it doesn't look at all the possible models. So it's sifting through based on the code. So it might not give you the accurate result or best result all the time. So it's better that you do the check yourself. That's why I had given you all instructions that at least estimate thrice before you start using auto ARIMA. Okay, so AR5 should probably be right for your data.
Ma'am, but the thing is, auto ARIMA should technically, if you don't define a max, then auto ARIMA should use stepwise regression, right? Basically, use a stepwise process, right?
It uses a stepwise process. You can force it not to use that. You can set stepwise to false.
Yeah, but ma'am, I have set stepwise to true. So it should eventually land on an AR5 model, right?
Not necessarily.
Okay.
See, if you set stepwise to true, it uses that sequential procedure which is there in the algorithm. It doesn't work that hard. So if you set stepwise to false, then it looks at more possible models. The number of models that it considers are actually larger. If you set stepwise to false, approximation to false, and then search. So that might give you a different result. You can check. I don't know because I don't know what exactly is the data you're using, but you can try that if you
Ma'am,
want.
my data is the unemployment data.
Okay.
India's unemployment data for the last 5 years.
Okay. So if
5,
you
6 years.
want, you can just check using stepwise false, stepwise equals false and approximation equals false. Then see
Okay,
if you're getting a different result from auto ARIMA. Okay, you just might.
and ma'am, if I'm not, then should I just like keep it as it is and then use the AR5 process for forecasting?
Yes, ideally you should be deciding that for yourself, but since based on what you discussed, I think it's fine.
Okay, ma'am.
Yeah.
Thank you, ma'am.
All right, let's take a quick break at this stage. Okay, so we'll meet in about 5 minutes. At 3:37, we'll meet. Okay, then we'll continue from there. hope all of you are back. Mr. Ramgopal, did you have any question? I think you were asking me a question. I'm sorry, I cut you
Yeah,
off.
I actually in that, you were trying to fit this model one on, you did that small regression, RPI on time, right?
Yes.
RPI on T. So there, if you just give a command T square, it automatically takes a 2 lakhs, is it? I'm sorry, I didn't know these commands earlier.
Not 2 lakhs, it's basically just squaring the data. So if I use this command, so this is nothing but T square. So I'll just plot, let me just type this. So you can see T was 1, 2, 3, 4 and so on up to 49, I think. So T square is simply the square of T. That's it. It's not a lag. Similarly, T cube is just T raised to the power 3. There are no lags involved. But we're just trying to fit a nonlinear trend here to the data and see which fits better.
Okay.
If you look at the graphs, I think you'll be able to understand better. Sorry, it's went ahead. So this is the original data, the index of residential prices. So in this, I can see that there's a trend. Now, either I can assume that there's a linear trend, okay, but it's not a perfect straight line. So first I tried with the linear trend. That seemed to fit the data well, but I hadn't added additional terms. So what I did in the second model was that I added the squared term and cube term. So here you can see there's a slight curvature here. It's not a perfect straight line. So this is from the linear trend model. When I try to fit a linear trend, you just get a straight line, which does, it's not bad for the data, but it doesn't capture the fact that there's a slight curvature. So once I fit this model, okay, which has the squared term and the cube term, that is better able to capture the trend in the original data. So you can see the slight curvature here. So this model seems to fit the data better in the sense that it's actually able to capture the pattern in the data better. So that's why I added those two terms, and we also checked the model results. So both were significant, T square and T cube. The coefficient attached to both were significant. So that's why we can rely on that nonlinear trend model, okay, better than the linear one. In case we found that the squared term and cube term had insignificant coefficients, then we could have dropped it and simply relied on the linear trend model. I hope that was clear to all of you.
Ma'am, can
Yes.
you show that decomposition again using seeds, the seasonal decomposition that you did?
Yeah. You want to plot the graph, is it?
Yeah, ma'am, we just decompose the trend and seasonality. Yeah, just 1 second if I can.
It's there in the code that I've sent you already. You're trying to run the command now, is it?
Yeah, ma'am, but it's giving me an error.
Okay.
It's saying that the argument does not exist for some reason. Okay, ma'am, got it. Thank you.
Fine. So let's move on to today's the part related to structural breaks in the data. So before we actually come to the modeling aspect of it, let's look at a couple of tests and some theory related to this. So originally in, I think 1982, I'll be sharing these files with you all, these PDF files. So these are certain papers which talk about structural change, unit roots and structural breaks. So what you'll find is that for many time series, especially if you consider a sample, a very large sample which runs over years and years, especially if you start from 1900s or 1800s and so on. Okay, so for many such time series, even for more recent time series, in certain cases you might find there's a structural break in the data. So if there's a break in the data, but the series, the time series that you're looking at is actually stationary, in certain cases only because of the break in the data, if you use standard traditional unit root tests, the test will give you the result that there's a unit root in the time series, or that the time series is non-stationary, because of which you'll end up differencing the data, taking the first difference and then checking whether it's stationary. If it becomes stationary, then you'll start working with the first difference form of the data. So in these cases where the time series is actually stationary, but there's a simple break in the data. For example, there could be a break in the trend, but once the break happens, okay, you'll find that the time series is stationary around the new trend line. Okay. So in this case, for this model that we are looking at, I'll just run that command again. So for example, this, if you're looking at the train one data set, there were some of the unit root tests, majority of them said that the time series was stationary. Okay, but some of them concluded that the time series is non-stationary, but that could have been only because of the structural break here in the data. Okay. For example, here around this portion, the time series could have been stationary around this trend line. Okay, if you look at this data, it would have been stationary around this trend line. Then after the break happens, again it would have been stationary, or it would have shown mean reverting behavior now around this trend line, which has a smaller intercept. Okay. So only because of a break in the data, the test could have been showing us that the time series is non-stationary, when in fact it is stationary but around a broken trend. Okay. So because of problems like this, where some people may reach the conclusion that the time series has a unit root, or that it's non-stationary because of breaks in the data. Okay. Certain research was conducted which showed this problem, which highlighted this problem, that most unit root tests have a strong bias against non-rejection of the null hypothesis of a unit root. Okay. So most of them will conclude that there's a unit root in the time series when actually there is no unit root, but instead there's a structural break, and otherwise the time series is stationary. So in 1982, okay, there were two individuals, Nelson and Plosser, who did some research which has become very famous. So they tested almost, I think, 14 macroeconomic time series, and they found that all of them, I think, except for one, there were 13 time series which were non-stationary, which had a unit root. And so they found that most time series, macroeconomic time series, are actually first difference stationary, or taking a first difference of the time series makes the time series stationary. Okay. So now this conclusion that they reached, and after their findings, you will find that many economists started taking the first difference based on the unit root test. If they found the null of a unit root could not be rejected, in most of the cases it could not be rejected, and they ended up taking a first difference of the time series. Okay, and that became stationary. So this was practiced until about 1989, when Perron, okay, the same guy who comes in the Phillips-Perron test. So this same person in 1989, he devised a test, and he said that it could be possible that the time series is actually stationary, but it just shows a structural break. So he devised a test to test whether his idea was correct or not. So let's look at the particular test that he used. So this is the standard ADF test. Now Perron also uses the ADF test, but he makes some sort of a modification in this test. Okay. Now I won't go into the details of it, but he specifies that there could be a break in the intercept or there could be a break in the trend in the time series. Okay. And the null and the alternative hypothesis were based on this idea of his. So the null hypothesis of his test was that the time series has a unit root without any structural breaks. Okay, this was the null. And the alternative hypothesis was that the time series is stationary, but it has a structural break. And the break could be in the trend or it could be in the intercept. So he had different alternative hypotheses, which basically allowed you to test any of these ideas that you might have about the particular time series in question. Now we won't be doing this test, okay? So we won't be implementing this test. After this, several tests were devised which actually built on this test. So you will find that in Perron's test, okay, he assumed that the break date was determined exogenously, which means that you know exactly when the structural break is happening, so you can test based on that. Okay. Whereas in most cases, you might not know when exactly the structural break is going to occur. Okay. It might be a very gradual break, or it could depend on several factors, so it might be an unknown break date. So his test results were based on this stringent restriction that the break date is known in advance, and then you can test the null and alternative hypothesis. Okay. Now, instead of this, based on or building on Perron's test itself, other tests were devised, such as the Zebot-Andrews test, which we will be implementing. Okay, and there are several other such tests. There are even tests for multiple structural breaks, but we'll do this simple one since it's used in most empirical research. Okay. So you'll find that Zebot-Andrews, they devised a test where you can determine the date of the break within the time series itself. It's not necessary for you to know the date of the break in advance. When exactly the structural break has occurred, even if you don't know it, you'll be able to run the test and determine if there's a structural break in the time series. So today we'll be doing this test itself. Okay, so this is an endogenous structural break test, which was devised by Zebot and Andrews in 1992. And it's a sequential test which uses a full sample. Okay, and it uses different dummy variables for each possible break date. So using this test, you can actually test whether there's a break in the intercept or whether there's a break in the trend, okay, or whether there's a break in both. You can check any of these. Here the break date is selected where the t statistic from an ADF test of the unit root is at a minimum or it's the most negative. Okay. Remember, for any ADF test, you'll find that you need the value of the test statistic has to be more negative than the critical value. Okay, that's one of the conditions. So if there's a structural break, if you find out the value of the t statistic when it's at its minimum, okay, that will help you identify the structural break instead of wrongly concluding that it might be a unit root. Okay. So a break date will be chosen where the evidence is least favorable for the unit root null. Okay. And they have also devised their own critical values for this particular test. Now in most software, you'll get the critical values being generated along with this test. So today we'll be implementing this test, and after this we'll look at other tests of structural breaks or detecting structural changes in the data. Okay. I'll mail these two files to you all. This is also similar. Okay, now one interesting thing was after Perron's test, for example, after Perron carried out his test in 1989, he checked the same data which was used by Nelson and Plosser. who had found that most time series are first difference stationary. So based on his test results, what he found was that only about 3 time series were actually first difference stationary or something like that, whereas all the others were trend stationary, in the sense that detrending the data could make it stationary. Okay? So the results are there somewhere in the test. Yeah. Okay. So using the Nelson and Plosser data set, what they found was if they do not consider structural changes in the data, they were testing 14 macroeconomic time series. Okay? And they found that 13 of them had unit roots, but they did not check for a structural break. And they found that only one time series was stationary, and that could also have a structural break. They weren't testing for structural breaks at all. Now, when it came to Perron, okay, he found that he was testing the null that there's a unit root without structural breaks. That was the null hypothesis. And alternative was that the time series is stationary but with structural breaks. And he was also assuming that the exact time of the structural break was known. Okay, so that's why it says exogenous with one break. So he was assuming for his test that the exact time of the structural break is known and that there's only one break in the time series, or only one structural change in the time series. So what he found using his test was that only 3 time series from the Nelson and Plosser data set actually had unit roots, whereas 11 of them were actually stationary with structural breaks. Okay, so the conclusion that Nelson and Plosser reached was actually wrong. Okay, that's what Perron found. And it's not necessary to actually take the first difference of most macroeconomic time series. Simply detrending the data might render them stationary. Okay. Then Zebot and Andrews, which is the test we'll be doing. So this is an endogenous structural break test, again, which looks at only one break in the time series. So by endogenous, it means that we do not need to know the exact time when the structural break happened. So it will be determined within the data itself. Okay? So once you run the test itself will tell you when exactly the structural break has happened, and it will look at only one structural break in the data. If there are multiple structural breaks, it will not be able to detect that break. Okay? The additional breaks, that is. So Zebot and Andrews, yes?
So, ma'am, does the Zebot and Andrews test will actually, in a sense, run dummy regressions for every date time point? So basically, if you have n time periods, will there be n regressions in which it will test that structural break occurred on this date or this date or this date?
Yes, I am not very clear about the exact procedure, but it tests several possible break dates and then identifies the one where the t statistic value is most negative. So I'll check that part again, whether it tests sequentially the way you are saying it. Okay, but it does check multiple possible break dates and then determines only one based on the result. I'll check and I'll get back to you in the next class. Okay?
Thank you, ma'am.
Yes. So Zebot and Andrews, again using the Nelson and Plosser data set, they found that instead of Perron's only 3 time series have unit roots, they found that actually 10 time series have unit roots and only 3 are stationary with possible breakpoints. Okay. So we'll look at, this was because they were determining the break date endogenously. Okay. So here again, if you look at the null and alternative, so Zebot and Andrews, if you see the star here, okay, so they assume no breaks under the null hypothesis of a unit root, okay, whereas Perron assumes a break. This is, I think this is wrong, all right, assumes a break under both the null and alternative hypothesis. Perron does not assume a break under the null. Okay, so this part has to be corrected, but the rest is the same.
Ma'am, excuse me, the null for Perron is first difference stationary, right?
Yeah, that there's one unit root in the time series and there are no structural breaks.
Okay, and the alternative is first difference stationary, or alternative is stationary.
Alternative is stationary with structural break, with a single structural break.
Okay, thank you.
So based on the Perron result, okay, if you fail to reject the null, that means that your time series has a unit root. So then you will take the first difference and make the time series stationary. Okay. So let's come back to the theory. And yeah, we'll quickly run the test results. Okay, I think I haven't added it here. We'll quickly go through the theory and then we'll look at this. Okay. Okay, so one thing I forgot to mention is about spurious regression. So somebody was asking me something related to this in the previous class. Okay, so that's why I've included this here. So many of you might be wondering, we had discussed this earlier, what exactly it means if a time series is stationary, and what is the problem if the time series is not stationary and then you go ahead and use it for estimation. Okay? So the problem, if you have non-stationary variables and you use them in a model for estimation, is that it results in something known as a spurious regression. Okay? So a spurious regression is one where basically there is no actual relationship between the variables in question, but once you estimate a regression, the model shows you results which indicate that the two variables are actually related. Okay? So this whole concept was developed by two economists known as Granger and Newbold in 1974. And they showed that using non-stationary time series for estimation can lead to serious problems in any regression. Okay, so what exactly did they do and how did they reach this conclusion? So they carried a simulation study. They did this for, I think, several thousands of times or something like that. They carried out simulations and they regressed two independently generated random walks on each other. Okay, so they took two time series or created two time series. Each time series followed a random walk. Okay. And these two time series were generated independently, which means that there is actually no connection between these two time series at all. Okay. Now we would expect that if you regress one time series on the other, the regression coefficient should not be statistically different from 0. Okay? Essentially, your regression coefficients should have a statistical value of 0, showing that there is no relationship between these two time series. And the R square from your regression should also be 0 or close to 0. Okay? Showing again that there is no relationship between these two variables, that one variable does not help to explain the other variable. Okay? But they found certain strange results. Okay? What they found was using the critical values of the t distribution. On testing the coefficients, the null hypothesis of a 0 coefficient was wrongly rejected very often. Okay? Which means that the coefficient value that they got from the regression, it was statistically significant, which means it was significantly different from 0, showing that there's some relationship between these two variables, when in fact there was actually no relationship between the two variables. Okay, so most of the time, if you take two non-stationary time series and regress them on each other, okay, what you will find is that you will find significant t values for the coefficients, and you'll also find a very high R square, or at least it won't be close to 0. So you'll generally find a high R square and significant t values for the coefficients from the regression, which indicates that these two variables are actually related, but in fact they are not related. Okay? The other thing related to such regressions is that most of the time, if you look at the errors from the regression, they will tend to follow a random walk, or they will be non-stationary in nature, and there will be significant autocorrelations in the residuals from your model, okay, indicating that there's something wrong with your model has been misspecified. Now the exact nature of the misspecification may not be known to you. It may be because you have regressed two non-stationary variables on each other. It could be because of structural breaks in the data. Okay? It could be for a variety of reasons, but it will generally indicate that your model is misspecified. If your model is good, if it is sound, then generally your model should be, the residuals from your model should be white noise. They should not show any sort of autocorrelation. The ACF should taper or very gradually go on to converge to zero. Okay? And they should have a mean of more or less zero and a constant variance. So your variables should basically, the residuals from your model should essentially be white noise in nature. But for a spurious regression, you'll find that they are not white noise, instead they are non-stationary. Okay? Now to avoid such spurious relations, most time series analysts suggest that you take the original series. Okay? If you find that it is non-stationary, you should make sure that through some transformation, for example, differencing the data or detrending the data, depending on the case, okay, you need to make your time series stationary and then use it for estimation. Okay? So once the transformation is carried out, you'll find that your time series becomes a weakly stationary process. So weakly stationary in the sense that the mean is constant and independent of time, variance is constant and independent of time, and again the covariance is also independent of time. So to avoid most of these spurious regressions, it's always recommended that you make sure your time series is stationary before you go on to the modeling part of it. Okay? Now the last part talks about the residuals, which I already mentioned. In the case of a spurious regression, the regression will become meaningless if the residual is non-stationary. Okay? Can anyone tell me, if the residual follows a random walk, why does the regression become meaningless? Or why does your model become meaningless? Why is it difficult to interpret it economically or attach any importance to the results from your model?
Ma'am, because as time is increasing, your results are getting less and less accurate. They do anyways, but in this case, your error itself is a function of time. So it will keep on increasing.
Yes. Okay. You're very close to it. Anyone else? Okay. What does it mean if the errors
Variance
are following?
is increasing.
Okay, yes, correct.
So basically, if the variance is increasing, we won't be able to forecast, like our forecast for further future will be very weak compared to our forecast for close by futures, right?
Yes, but that happens in any case.
Yeah, but that will
Just,
happen because we are using forecasted values for the next periods.
okay. You are correct, but in any case, for any forecast, you'll find that the variance of your forecast errors, it keeps increasing as you forecast further along the time horizon. Okay? The reason is that if the residual follows a random walk, remember what it means if any time series follows a random walk. It means that errors have a permanent effect on the time series. The impact of the error does not die out. Instead, it keeps affecting the time series over and over, and the impact will be permanent. So there'll be a permanent shift in your time series which occurs in every time period almost. Okay? So that's why if the residual is non-stationary or if it follows a random walk, it means that the impact of the errors don't die out at all, and basically your time series is like you said, forecasting will become very difficult, but even just interpreting your model or the results from your model will be very difficult. because each error has a permanent impact. So how do you know whether the fitted values from your model are adequate or not? Okay. So because of the impact of these permanent errors, that creates a problem in the case of spurious regressions. Okay. But one thing to note is that in case there are special cases. If you find that two time series are non-stationary, okay, and you regress them on each other, but the residual from your model is actually stationary, this could happen. So this happens if the two variables are co-integrated. Though this is something that we'll be studying later on, where you can regress two time series on each other in the special case where the residual from the model is stationary. Okay? That regression is fine and you can draw certain conclusions from it, okay? Because it generally talks about equilibrium relationships between variables and so on. That is something we'll discuss when we're discussing co-integration. Okay? So we'll come back to that aspect. But remember, if you run a regression with two non-stationary variables or multiple non-stationary variables, and you find that the residual is non-stationary from your model, that is a problem. And that is a case of a spurious regression where you cannot rely on the results from your model and your regression is basically meaningless. Okay? So I think we'll quickly look at one example of this. Okay, so this is for a spurious regression. This is different from the rest of the exercise that we're doing. Okay, so I'll just clear this. No, actually I won't clear it. I'll run it as it is. So T series is in our library already. We've loaded this package already. Let's just we want to create around 1000 observations. Okay, so that's what we're doing in this command. Now in this next command, what we are doing is a simulation. So before any sort of simulation exercise, you need to set this command. Okay, so you need to set seed and put any number. You could set 1, 2, 3, 4, any number. But basically, once you set this command or once you put in this command, what it does is every time you run this simulation, for example, when I run the next set of lines for the code, it will give me the same results every time I run the code. Now, suppose I don't run this command and instead I keep going ahead and running the next few commands. Since it's a simulation, every time I'll get different results from my exercise. Okay? So to make sure that you can reproduce your results, what you need to do is set seed and put some number in. You can put any number. Okay? So type this command and then go ahead and run the rest of the code. Now what we are doing in the next command is we are trying to create a time series with 1000 observations. Okay? Now essentially this time series will have 0 values. So if you, after running this command, if I type y, then you will find that it only has 1000 zeros in it. Okay, this object which I have created. Okay, let me just show you. Okay, so this has got 1000 zeros here. Okay, that's what we're doing. We are trying to create this time series, which is a non-stationary time series. Okay, and then in the next line of code, what we are doing is creating the error term for this particular time series. Okay, so we are creating the error for this time series y. Okay. So you're drawing it from a normal distribution and again you want 1000 errors. And you're telling R that these errors are actually time series. Okay, so now we've created the errors here. Now let's run the next line. So we are generating this time series, which is basically a random walk. So yt depends on its first lag. Okay, and this is the error associated with the time series yt at time period t. So we are creating this time series, which is basically an AR1 process. Okay, and it's a random walk since the coefficient of y here is 1. Okay. If I had put some other number here, for example, if I had put 0.6 or 0.5, then it would not be a random walk. Okay. So this helps me create the time series y. Let's just plot this and see what it looks like. So this is the time series, okay, that we have generated. It's a random walk. You can see there is no tendency for mean reversion here. Okay, it keeps drifting.
Ma'am, could you just give us 1 second to read that?
Yeah, sure.
Just 1 second. So our first value starts with 0 itself.
Sorry?
Our first value starts with 0 itself.
First value.
Y.
Yeah, yes, correct.
All right. And then the whole process starts where it depends on the previous term and plus
Yes.
a small error.
Yeah, correct.
All right. And ma'am, this normally distributed distribution, are we assuming that the mean is going to be 0 and the SD is 1?
We'll plot the errors, then you'll see. It's creating
Alright.
a white noise series. Okay.
No, ma'am, actually in that VY TS R norm T.
Yes.
So when we're using R norm, that R norm, usually we specify the SD and mean, the mean and the variance. So out here, so if we don't specify, we'll get 0 and 1. Is that right?
Let me just check. The mean is definitely 0. I'm not sure about the standard deviation. Okay, so I'll just quickly check. I don't know if this is the command. Yeah, it's approximately 1.
Yes, ma'am. Thank you, ma'am.
Okay, so this is a plot of the errors, okay, that you are getting from this AR1 process, and you can see that it resembles a white noise series. Okay, the mean is 0. We just check the standard deviation is approximately 1. Okay, so we plotted the errors and the time series itself. Okay, now let's create another non-stationary time series using similar commands. Okay. So again, since it's a simulation, okay, set a different number so that you don't get the same set of values. So run this command, set seed, okay, so that you can reproduce the results every time you do this exercise. Now create a time series which is x. Okay. We're denoting the time series as x. Again, this just creates 1000 zeros, okay, that are there stored in this object x. After this, we'll generate the errors. Okay. So we're trying to create white noise errors again. Then we are creating this random walk process again. Okay. Note that the coefficient associated with the first lag of x has a value of 1. Okay. So we're creating a random walk series again for x. Okay. So next, let's just plot the errors. Okay. You can see this is white noise again. Let's quickly check the standard deviation. Do it here. Yeah, approximately 1 again. Okay. So once you've plotted the errors, just plot the time series itself. Okay, so this gives you a plot of the time series. Now what you have to note is that both have been generated independently. Okay? So we did not use y to generate x, or we did not use x to generate y. So they are actually independent time series. Now let's just select a portion of the data set. Okay, you can do it for the entire exercise if you want. Sorry, for the entire 1000 values. But here we are just selecting around 700 values, okay, to run our regression. So we are specifying that y is time series and we want to use only the 700 middle 700 values of the time series. Similarly for x, okay. So we want to use values from 300 to 1000. Now let's plot both x and y. Okay. Now in certain points or certain pockets, you will find that they seem to be moving together, okay, in some fashion, but actually they are independently generated. Here you can see the divergence. Okay, but in certain cases, you might find that they tend to mimic each other, which is completely random. Is my voice echoing by any chance?
No, ma'am, it's not echoing.
Okay. So once we've looked at the time plot, okay, let's run this spurious regression. Since we know that these two time series are being generated independently, let's run the regression. Okay, and let's look at the results from the regression. Okay, so as predicted, you'll find that although there's actually no relationship between these two time series, the coefficients of your model are actually statistically significant. Okay, they are highly statistically significant, in fact. Okay. And based on the F statistic also, you'll find that you need to include these coefficients in your model. Now let's look at the R square from your model. Okay. In this case, it is quite small. Okay, but it's not equal to 0. That's something that you need to keep in mind. Are you all getting the same results as me, or is it different?
Ma'am, I'm not doing it. I'm just following you.
Okay, fine. Once I share the script, just check if you all are getting the same results or if it's different. So this is a summary, and you'll find that the R square is significantly, we haven't tested the statistical significance, but if you used a F test for it, you could probably do it. Okay, but it's not equal to 0, the R square value. In addition, you find a significant t value for your coefficient. So this is a case of spurious regression. Now let's just check the errors, okay, from your model. So if you just look at a plot of the errors, this does not seem to be stationary. Okay, if you look at just this portion, it might seem stationary, but if you zoom in, you'll see that it does not appear to be stationary. Then if you look at the ACF of the errors, okay, first let's just create the errors itself instead of using such a long command. Okay, I'm just creating a variable for the errors. Okay, now if you look at the ACF of the errors, you can see that you have significant autocorrelations which do not die down even after 25 lags. Okay? So the residuals appear to be significantly autocorrelated based on the ACF itself. So your time series is, sorry, these residuals are non-stationary. Okay? That's something you would have understood by looking at the ACF. For any stationary time series, you'll find that the ACF, it quickly dies down to 0. Okay? Or even if it's more gradual, after lag P, for example, if it's an ARP process, after lag P, you'll find that the ACF, PACF in that case, will die down very quickly to 0. It will converge very quickly to 0. If you want, you can also plot the PACF and see what sort of results you get. Let's check based on the Dickey-Fuller test, whether we are finding that our errors are stationary or non-stationary. Okay. So I'm storing my test results in T1, this object T1. I'm using the package URCA, okay, to carry out the ADF test. Now here, if you look at the value of the test statistic, in this particular case, you find that you are able to reject the null at the 10%, 5%, even at the 1%. If you consider that this is minus 5.884, okay, you are able to reject the null. Let's also check in the case of a drift, okay, what sort of result we are getting. Okay, so if you include the drift term, okay, which is probably more likely if you look at the plot, here you find that you are able to reject the null at the 10% level, okay, but not able to reject the null at the 5% level and 1% level of significance. Okay. Let me just check with trend also. Okay, so if you assume that your time series has a stochastic trend here, okay, then in this case you are failing to reject the null of a unit root at 1%, 5 and 10%. Okay. So I'm not exactly sure which one of these would be appropriate. Okay. If you look at the plot of the residuals itself, either including the drift would be appropriate or including the trend. Okay. Since there is an upward trend, you might want to include the trend component. Now let's check whether differencing these errors actually makes the time series stationary or the errors stationary. So here I'm going to use the command none here, okay, not including the drift or trend. So here once you look at the results from the test statistic, okay, you find that you are able to reject the null at the 1%, 5% and 10% levels of significance. Okay, so you're concluding that your time series is stationary once you take the first difference of the errors from your spurious regression.
Ma'am, could you please plot the difference of the errors?
Yes. Okay, so this appears to be stationary once you take the first difference.
So this drives home the point that this is like a spurious one.
Yes.
Because okay.
Because you found that the errors were non-stationary from your model, and then once you took the first difference, they become stationary. Okay, so this is an example of a spurious regression. So in most cases, if you take two non-stationary time series and regress them on each other, you'll find that the errors are non-stationary. You can diagnostic checking of any model involves checking the residuals. So if you find that the errors are non-stationary, it means that your model is misspecified in some way. It might not always be that the time series is non-stationary. It could also be because of a structural break in the data and so on, okay? Or some incorrect transformation of the data. Okay? Maybe you detrended the data instead of differencing it or something like that. Okay? So any of these cases could lead to errors which are non-stationary, which will give you some indication that your model is misspecified. Now, the only case in which you can take two non-stationary variables and regress them on each other, that model will be valid only if the errors are stationary, which happens in the case of co-integration. That's something that we'll discuss later. Okay? So we'll stop here for today. Any doubts or questions?
Ma'am, may I ask a doubt regarding my project, if that's fine with you?
Yes.
All right, then I'll just wait if anyone has any doubt regarding the class.
Does anyone have any doubts related to today's class? What was taught in today's class? It doesn't seem to be. The rest of you, if you want to leave, you can leave, right? Yeah, you can go ahead and ask your doubt related to your assignment.
Yes, ma'am. So, ma'am, I was working with population data for US on a monthly basis. Now, after I took the first difference using DF test, KPSS test, and using uh, one I forget the name. Let me just open my codes. Yeah, PPP test. The three of them, it showed that the difference equation, the difference version of it was stationary. However, when I went to plot the ACF and PACF, the ACF did not seem to die down very quickly, and all the values were incredibly high in the differenced one. The PACF looked exactly how we would expect it to be. So I'm a little confused because when I worked with zero difference, that time it was showing non-stationary, and when I worked with first difference, it was showing stationary. But then the ACF and PACF were not acting like they were supposed to act.
Okay. One command that you can use, did you try this ndifs? For example, if I take ndifs R1, it gives me 1. Okay, so that will tell you how many times you have to difference your time series to make it stationary. So just try that command once. Again, it's based on these similar tests. You can try that. Okay. Then another thing that is possible, if you want to share the images that you have, you can do that if you want.
Ma'am, in NDIFs it's saying we should go with 2, and that is also the model I had later on decided on.
Okay.
NDIFs is 2.
What did you say your data was? Population data.
Yeah,
for US?
population data, monthly population data of the US.
Okay.
From 1951, but I've taken only from 1995.
Okay. When you plotted the data, did you notice any sort of structural break or anything?
There was this one kink in the middle. It felt like it jumped, but otherwise it felt fine.
When exactly was that? What was the time?
2010.
2010. Okay. Okay, just check. It's just a hunch, but just check if there was a lot of immigration or something into the US around that point of time.
Ma'am, possibly that the 2008 crisis had just happened, so maybe that's why. Actually, ma'am, the data did not seem to have a break, but the difference and the second difference like had a fall out there.
Okay, it would help if you could actually show me your graphs.
Yes, ma'am. May I share my screen?
Yes, 1 minute. Let me just stop sharing mine. 1 second. Yeah.
So I'm just 1 second. So okay, ma'am. So all right, I'm a little confused. Hold on. My plots are all here. All right. So ma'am, so this is my PACF. This is my, now I think you would like to see the. I'll just write it down instead of. So this is SATS, which is, this is what the data looks like once I remove the seasonality. And if I go for the first difference of this, then we notice that around 2010 there's like a sharp dip.
Okay.
And the same with 2.
Okay, so when you plotted the original time series, after you seasonally adjusted, there was no such dip, right?
Yeah, this is what I was getting. It didn't look like a dip. But then again, we are looking at from 1995 to 2020. So maybe the 2010 is somewhere out here, ma'am. You can see it's plateaued for a while.
Okay. See, one thing, maybe you can take logs, all right? Since it's such huge numbers, you can just compress the data a bit by taking logs.
All right, ma'am.
Another thing, can you move up? Did you do any sort of transformation or anything?
No, ma'am. Just differencing.
Okay.
I removed the seasonality. I mean, and I kept. I just did a differencing because I had realized that I have to take at least one difference or two difference, and both the models gave. So, ma'am, I chose two models. One was M4, which was with two differencing, and
Okay.
M7, which was with one differencing, and
Okay.
both of them were giving me pretty good results. So if I use
Okay.
M4,
Hmm.
just so I am within the bounds, and I'm like right in the center.
Yes.
Same
Your
with.
forecasts look very good.
Yes, ma'am. But given the fact that they're both on different thing, because I'll so M4 I think I've mentioned out here is 1-1 and M7 is 1-1-1.
Okay.
So I'm a little confused because the ACF and the PACF don't really. I mean, I'm not very happy with how the PACF and the ACF look.
Okay. So you're saying in what way are these two models similar?
I'm so sorry. This I've written just colloquially. They're similar with respect to their AICC, with respect
Okay.
to
Okay.
everything else.
Fine. What about forecasts?
Both the forecasts seem to work pretty well.
Okay. Graphically, no? Yes.
Yes, ma'am. Graphically.
Okay. What you can do is that accuracy command is very simple, right? So
Yes,
just
ma'am.
use that. Okay. And then select one based on the accuracy. Whichever has better forecast accuracy, you can choose that.
All right.
I won't evaluate you for this, but this is just for yourself so that you can choose between these two models.
Okay. So ma'am, basically, if I have to, then I can use it. I can work with logarithms, but now it makes sense because I think whenever we're talking about population, and we quite often use logarithms because of the exponential nature of it. All right. Yeah. And okay, ma'am, I'll try using accuracy.
Okay.
The ACF, PACF won't cause an issue, right?
Uh, can you tell me when your plot of the residuals that you are finding that in your ACF and PACF, or where exactly did your ACF show a lot of autocorrelation? Just take me back to that plot.
Yes, so I will have to just okay. So this is so, ma'am. Do you want to see it with difference too, or with how many differences? Do you want? Okay, no. Once again, you want the ACF, PACF, right? So
Yeah.
case yeah. One thing I'll just need to look. I've kept the code somewhere here. I'm not very sure where I have. I think it's GGTS display. Yeah. Yeah. So the ACF looks like this, which is not something very ideal.
This is when you take the second difference, right?
Yes, this is when I take second difference, and if I take the first difference, and it still looks like this.
It's very strange. I don't know why your ACF has this appearance.
Yes, ma'am.
How many observations do you, if you run it only up to this point, up to 2010, then what happens? 2010, you're noticing the break for both cases, right?
Yes, ma'am. Actually, I've actually deleted a lot of data from 1952 to 1995.
Okay.
If you want, I can include some of that, and I can remove, and I can work in the 2000 to maybe 2000, 2005 to 2010. I can try to predict, and I'll delete everything post 2010 so that we can skip
You
with
can
this.
do that, but looks like you've done a lot of work, so I suggest that you stop, otherwise it'll be
Okay,
too
endless. Yeah.
much. Yeah. What you can do is, once we cover structural change in the next class, then you can continue using your data set for your own, what do you say?
Okay, madam.
Yeah, for your own, so that you learn more about how to handle data.
Okay, ma'am. Thank you, ma'am.
You can stop with this, all right?
All right, ma'am.
I'll try and figure out why this is happening. One possible reason is that it's a near unit root process. Okay, then in that case, it might have this sort of appearance, ACF. So if your AR1 coefficient is very close to 1, that might be the
Okay.
reason why it's happening. Otherwise, right now I don't have any other explanation for it. I'll look into it.
Yes, ma'am. I think my AR1 is near. Okay, it's not that.
No, it's small.
Which one is this? M4. All right, all right. Take care. I'll try to figure it out.
Okay. All
Thank you,
right.
ma'am.
Thank you.
Ma'am, can I ask you a question on this?
Yes.
Uh,
Okay, those who want to leave, please leave. You don't have to stay back.
Thank you, ma'am.
You're welcome.
my query is that in this kind of data,
Hmm.
does it make sense to deal with growth rates rather than absolute values? Typically, like
Yes.
population or
Actually,
GDP.
using the growth rate will make it stationary. So when I think he left already. Yeah. So one of you, or I'll mail him. So one thing you can do is taking the growth rate will make the time series stationary itself. So you can just work with growth rates, and that's why I suggested logs also, that will compress the data. So yeah, taking growth rates will make more sense. Even for GDP and so on, most people tend to use growth rates because taking the first difference, which is essentially similar to taking a growth rate, will do the same trick.
Okay.
Ma'am, may I?
Yes.
Actually, you have highlighted my name in the list, and I'm not sure.
You'll need
Check
to
that.
check the comments. Okay, check the comments in the Google Sheet. You'll know exactly why it's been highlighted. Then you can make the change, and I'll
Ma'am,
remove the mark.
I'm really sorry, but the thing is, I can't find. All right, I'll try them. I'll try checking it. Thank you, ma'am.
Okay. It's probably something to do with the fact that you have not specified your data. Okay, which
Right,
country, or
understood, ma'am.
yeah, something like that.
Sure. Sorry, thank you.
All right. Thank you for your time then. Okay, let's end the meeting.
Thank you.
Thank you, ma'am.
Thank you. Good day.
Thank you.